Everything seems to be quite peaceful today in the laboratory. But wait, what is this? Oh, just a wild PCB. Or a board. Doing its work. Just being silent. Not being noticed at all. Unless we decide to take a closer look. I wonder what are all these components doing over here? Quite interesting. Some communication going on. And of course, power is flowing through it. What about these lights? Let's make an experiment. Let's take a timer for 1 minute. And we're going to measure a signal with a multimeter. Let's turn it on, and of course we need to connect it properly. In order to draw the data that we're collecting, let's draw an axis to represent time. On the vertical axis, we are going to represent the values of the signal. In this case, voltage. So, as we said, we were going to take measurements every minute, so here we are, and let's write it down so we don't forget the units. For the amplitude or the values of the signal, let's assume we're going to take a maximum of 6 volts. And let's start it up. Time to take the first measurement, and we see it's around 2 volts. So let's proceed with the following one. Okay, it seems that we are finished. So this is the result. But let's draw some lines to see it better. What this signal is about. Okay, it's interesting, but kind of hard to understand what's going on in these minutes that we are waiting to take the next measurement. So let's reduce this time. Let's use 5 seconds. And let's start it up again. Here we have the last point of our signal, and we can see that makes more sense now, but I think we could make it better. Let's reduce it to 1 second, and let's try to take measurements every second. Sadly, it seems that, it's too fast for me, cannot do it. Luckily we have this instrument here, this is the oscilloscope. Let's compare it to the first trial. Quite different. What about the second one? Yeah, this looks more like it. But this signal is a lot faster too. The oscilloscope is composed by the display. In this case, the horizontal axis is the time and the vertical axis is the amplitude, just like our drawings. With these controllers, we can select the position of the signal vertically and also the amplification, that is, how many volts per division. With these controls, we can select the position of the signal horizontally, and also we can select the value of each division of time, in this case 200 microseconds per division. The trigger control is kind of an advanced control, but it means the synchronization of the signal with the oscilloscope. So let's try to make a first measurement with this probe. Let's take this red light over here because it looks to be always on. But we see that it takes 2 milliseconds on and 2 milliseconds off. What about this blue light over here? In this case, we can see also the frequency is the same, but the voltage is quite higher. What about this pin over here? It is kind of quiet, but we have a signal of 50 MHz. The oscilloscope is also useful when we want to try and prove our designs. Here we have a low-pass filter with a cutoff frequency of 15.9 kHz, but we have to test this in order to check if it is true or not. So we're going to use our signal generator. It is configured with 1 kHz in 2 volts peak to peak, and this is the circuit. We are going to connect here the input, the channel 1 of the oscilloscope, and the channel 2 here on the output. What we see on the screen is that both signals, the input and the output, are the same. That is because the frequency of the signal is lower than the cutoff frequency of the low pass. So now let's check it out with the 15.9 kHz. The same voltage, 2 volts peak to peak, and here we have the same circuit, channel 1 and channel 2, and this is the result. The small signal is the output. As we can see, it is on the -3 dB point of the cutoff frequency, which means it would be 707 millivolts, but the oscilloscope shows 705 due to its resolution. So this was the oscilloscope. I hope you have a good understanding and see you next time for other videos.